So a few things before starting. Enjoy the weather, I guess. The last problem set will be the 9th problem set. So I jettisoned one. Problem set 9 is a simpler it's a individual question problem set due on Friday, just to get you to think a little bit about the nuclear physics we're doing right now and a little bit of the modern physics, the leading part of it that'll start on Wednesday. About Orion, I get endless questions about Orion. It's turned out to be much more hassle than it was intended to be. Just make sure you've done a good number of Orion questions, and I'm likely to give 100% for 20 times about 7 or 8 chapters. Hopefully you will have done somewhere in the mid 120, 50 those Orion questions, and that'll do it. I'll call that, I'll try to give you full credit for that. Okay. The missing 10th problem set I'll deal with in some generous manner also. I will remind you that at some point there is a course evaluation for this course, and if you complete that before its due date, and it's due sometime during finals period, so don't wait too long, I drop your lowest problem set score, so I don't average it in. Yeah, John?
When does it appear?
I don't remember when it appears. It could be almost any time, but I know it's due before the final. So I will try to send a warning to people who haven't done it. I get the list of the people who have completed it, but that's all. I don't think it's up now, but I'm not sure. It's on Colab. It's on the main page of Colab. You don't have to go into this class. You just, when you log into Colab, there are course evaluations in general there, and they appear at some point very soon, and you can just do them all. Any questions about course stuff? Okay, well, where I left off with nuclear reactors or nuclear power generation was the idea that it is possible to make a chain reaction occur in essentially natural uranium, but you have to be tricky about it. If you think back to the story of nuclear weapons, there are in nature a couple of fissionable nuclei still in existence, left over from long, long ago. They've been hanging around ever since. Some star explosion way back when. Uranium-235 is one. I think there is a thorium isotope that works. But basically, the fissionable nuclei are very rare in nature, and they're typically a small fraction of a naturally occurring element, and therefore very hard to get hold of. So uranium-235 by itself, it's rare. It's less than 1% of naturally occurring uranium. So that's part of the reasons why nuclear weapons, the proliferation of them is not simple. It's a big undertaking. It's sort of these national projects, for better or worse, to try to build nuclear weapons. The starting point, I think, has to be, I mean, with exotic exceptions, has to be the separation of these rare fissionable nuclei from the rest of the nuclei, so that you get enough of them together that you can start making chain reactions and weapons. But for nuclear power, that process of separating out nuclei is too hard. It's too much work, too expensive, not cost effective. So nuclear reactors try to operate with non-enriched materials or lightly enriched. It turns out a lot of reactors operate on slightly enriched uranium, for example. It's not naturally occurring uranium. It's uranium from which maybe half of the uranium-238 has been removed. And removing a little bit of the uranium-238 is obviously a lot easier than trying to remove all of it. The difficulty of removing, I'll remind you, is because they're chemically, uranium-235 and uranium-238 are chemically indistinguishable. They differ only in mass, and it's only about 1% difference. So it's like you're just having thousands of identical looking cars, Mini Coopers, coming down the road, and you're trying to find the one that has the upgrade package that adds 1% mass to the Mini Cooper. You steer them one way, steer them the other way, depending on this tiny difference between them. It's a hard job. And that, if back in the second Gulf War, the concern about, well, I mean the Gulf Wars in general, the concern about, or Iran, the concern about centrifuges being in some of these countries. Why the centrifuge? Because a centrifuge, where you whip things around in a circle, you're sensing mass. The act of making something travel in a circle, if you remember, it well, it's the other class really, the fall semester that we do that in some detail. Movement in a circle is an acceleration toward the center of the circle, and it requires a force, and a more massive thing trying to go around a circle takes a larger force toward the center than a less massive thing traveling in the same circle. So they use centrifuges to try to in effect, to measure the mass atom by atom of uranium-235 versus 238 and send the 238 packing and keep the 235. And in this sort of process, you end up with a lot of leftover 238 that's not so interesting, and that's so-called spent uranium from which the 235 has been removed, and it gets used for other random things. It's a very dense material, for example. It makes lead look light, so it has uses. Anyhow, back to reactors. The reactors, you don't want to do this whole heroic effort of separating 235 from 238. So what do? They use a trick whereby they make the uranium-238 semi-invisible. It turns out if you take the neutrons that are released by the fissioning 235 nuclei, and you, as quickly as possible, slow them down to ordinary speeds, the speed of thermal speeds, the speed of gas atoms, for example, in this room, which is fast but not super fast. They no longer interact with the uranium-238 nuclei. The uranium-238 nuclei just let them go past. It seems odd that particles that are traveling past each other would care how fast they are traveling to determine whether or not they hit. That's not a classical notion. The classical notion is if two cars are coming along and they drive through the exact same center of the intersection at the same time, they're going to hit, right? It doesn't matter whether they're going 2 miles an hour or 100 miles an hour. Quantum mechanically, that's not the case. There are waves going on here, and it's more complicated interaction. And it turns out that a neutron traveling past uranium-238 nucleus doesn't do anything to it. Just passes right on by if it's going slowly. If the neutron's going slowly. If the neutron's going fast, there's a significant chance that the neutron will be absorbed by the uranium-238, which will then turn it eventually into plutonium-239. All right, so the trick that's used in nuclear reactors is to slow down the neutrons. The reactor then operates on slow-moving neutrons meandering through the material, hitting uranium-235 nuclei, breaking them, and launching new neutrons out into the milieu, which are then slowed down, wander around, bump into uranium-235 nuclei, and break them too. That's the chain reaction in what's called a thermal fission nuclear reactor, which is the vast majority of nuclear reactors in the world. The slowing down process is done by what's called a moderator. They're just little nuclei that slow down the neutrons by just billiard ball kinetics. They just hit each other. And a fast-moving neutron hitting a small nucleus, for example, the proton inside a hydrogen atom, they'll do that. You remember the toy? I haven't brought it out this semester. The toy that has the balls hanging, and you take the last ball and you let it swing into the row of balls, and nothing happens to the middle balls, but the last one pops out. So one goes in, smack, and comes to a stop, and the one at the end jumps out afterwards. That's just a transfer of momentum through the whole stack, and out it comes in the last ball. So the point of this is that a neutron coming along, hitting a proton head on, that neutron will pretty much come to a stop, and the proton will go off carrying the energy and momentum that used to be in the neutron. They have almost the same mass, so it's almost like two balls hitting each other. Neutron's a little heavier, a little more massive. So protons make a great moderator, which is to say hydrogen atoms, the little nugget at the center. The electron is unimportant in this. It's the little nugget at the center, which is a proton, that does the slowing of the neutrons. I think the next slide is a list yeah, well, here's the list. So hydrogen nuclei as moderators, dandy, because well, they're very good because the mass match is so good. So the flying neutron hits that proton, and there's a really beautiful transfer of motion from the neutron to the proton, and the neutron now is slow. You've got a fast-moving proton, but that's not so interesting. It's charged. It's not suitable for causing subsequent fissions. So the energy momentum transfer is great. There's one flaw in using protons as moderators, which is, say, using hydrogen as moderator. It's got a slight chance of absorbing the neutron. That proton and neutron can get together and form the nucleus of a deuterium, or heavy hydrogen atom. And that means that hydrogen has a small opportunity. It depletes the neutrons a little bit. And that is enough to cause a little bit of a problem. We'll come back to it. What's another suitable moderator? Deuterium, which is the heavy isotope, the naturally occurring heavy isotope of hydrogen. I should know what fraction it is. It's less than 1% of hydrogen atoms, but it's there. You've got deuterium in you. Its nucleus is a pair. It's a proton and a neutron. So it's twice as massive, pretty much, as a normal hydrogen nucleus. And when a neutron hits that, the match of mass isn't quite as perfect. So you might have to hit two deuteriums. Hit one, and it gets somewhat slower. Basically, the neutron's going to bounce back because it's hitting a heavier thing, a more massive thing than it itself. So it'll bounce back a bit, and it might have to hit a second deuterium nucleus to really come down into good slow speed. The advantage of deuterium, however, is it never absorbs a neutron. It's just perfect. The neutron bounces off it, never sticks. And therefore, deuterium is probably the best moderator. As a result, there are major efforts around the world to purify deuterium for use in nuclear energy of all sorts. So during World War II, there were deuterium or heavy water plants around that were issues. They show up in novels now, talking about trying to bomb the deuterium plants and stuff. Deuterium is part of the nuclear infrastructure, is purifying this stuff. It requires high technology too, because its only difference from ordinary hydrogen is its mass. Chemically, it's like hydrogen. One electron. It does all of hydrogen's chemistry. It is, however, twice as massive as ordinary hydrogen, so it's a bit easier to separate it from its lighter sibling than trying to separate the two uranium nuclei, which only differ by 1%. There's a big difference in these in the isotopes of the low mass elements are relatively easier to separate. And there is actually, well, for medicine, there's a lot of isotope separation that's done. Medicine and various biomedical research, having specific isotopes is often useful for marking molecules to watch them move through some biochemical process. All right, so deuterium, separating deuterium. Deuterium is a great moderator. It's quite expensive, requires serious effort to obtain, but okay, probably the best moderator. Third choice, carbon. Carbon, it makes a decent moderator. It's considerably more massive than neutrons. The nucleus of carbon, carbon-12 is the standard. It's sort of 12 times as massive as a neutron, the typical carbon nucleus. So you have to have more collisions. A neutron has to hit more than one carbon to really slow down a lot. And what else about it? It does not absorb neutrons well at all. So it's pretty good. It's a solid, which is kind of convenient, but it does burn, which is kind of inconvenient. So you got to be a little careful with it. And eventually I'll talk about the famous nuclear accidents, and carbon has played a significant role in several of them. All right, so deuterium's rare. but a great moderator. Hydrogen, next choice. Carbon is third choice. Oxygen seems to be unimportant. Neutrons don't hit oxygen. So the hydrogen usually shows up, and deuterium also, as water. And water, so water acts as the moderator. Water can also act as the heat exchange system. It carries heat from the nuclear reaction into something else to generate electric power, for example. So water plays a central role in a lot of nuclear reactors, both as a moderator to slow the neutrons down and as the carrier of thermal energy, which ultimately is used to generate electricity. All right? All right. So the basic, at this point, the basic idea is this, that you can have a whole huge block of essentially natural uranium. You slice it up and you intersperse moderator into this. So you might have, instead of one giant solid cube of uranium, you might have rods of uranium immersed in water. The water will be the moderator, and also something to do with the heat. And the rods sitting in there are the fissionable material, most of which is, they're mostly uranium-238, which is useless, but at least it doesn't have much, doesn't participate much. When one of the uranium-235 nuclei in one of these rods fissions, its neutrons zoom out. They go out of the rod. They might hit something on their way out, but there's a very good chance they would make it out of the rod into the water. And they hit something in the water, slow down, and now they're slow-moving neutrons. And they meander around. It's pretty fast meandering, but they're binging around through the material, and they hit another uranium-235 nucleus and shatter it. And out go fast neutrons that then promptly slow down because they hit water, and so on. And you can get a chain reaction in this. The chain reaction can, if one initial neutron on average will produce a little bit less than one subsequent neutron, which will produce a little less still than one neutron, you'll have a chain reaction that will fizzle out. If, on the other hand, you have one neutron begets 1.1 neutrons, begets 1.24, now you've got a building chain reaction that you have to be careful about. That's something to be worried about. Although you kind of want it, but you kind of don't want it. You want the chain reaction to develop, but you don't want it to get out of control, so that too much is happening too fast and it gets overly hot. Incidentally, as these neutrons come flying out, along with all the other shrapnel that comes out when a uranium-235 escapes, collisions very quickly turn that energy into thermal energy. So it comes out as flying projectiles, which have kinetic energy, but very quickly things bounce off each other and it becomes thermal. So the temperature of the whole system starts going up as you get the chain reaction going more and more. All right? Any questions at this point? This code of silence has really settled in. The rain and everything. Of course, with the good weather, I blame it on the good weather. All right, so you've got these, you can get a chain reaction going. How do you control this chain reaction? If it dies away, that's easy and not a problem. One uranium-235 fissions, and it might cause one subsequent fission, which might cause one more subsequent, but there's a good chance that nothing will happen and it'll stop. But if it starts building and building and building, now you have to worry about it. And it turns out that there is a natural effect that assists control of thermal fission nuclear reactors. And that is that when a neutron hits a uranium-235, it can cause an immediate fission, or it can cause delayed fissions. In fact, more accurately probably is when one neutron goes and causes something to go pop, a certain number of neutrons are on average, are subsequently released into the system. So maybe 2. But of that 2 neutrons, 1.9 of them come out immediately, and 0.1 of them are delayed. They show up over the next 20 minutes or half an hour or maybe a day. For example, where would that be? Well, if part of the neutron calculation, the spreadsheet, where one neutron gets you 2 on average, but if you actually break that 2 up into all the possibilities, well, some of them come immediately flying out of a breaking uranium-235 nucleus. But a couple of them show up, a small fraction, show up from a radioactive decay of one of the fission fragments from uranium-235. So uranium-235 breaks into pieces, which include neutrons, and those go into the immediate, the prompt neutron tally. But then there's some radioactive elements created, radioactive nuclei created, and those may release a neutron later, maybe half an hour from now on average. So those show up in the ultimate calculation of how many neutrons are produced in each generation, but they're slow to show up. They come in way later. And as a result, there are 2 different types of chain reaction ideas. One is, or I should say, critical masses. The explosive chain reactions that we've talked about with nuclear weapons involve what is called a prompt critical mass. That is, using only the neutrons that show up immediately after the shattering of a nucleus, you're still able to have a growing number of neutrons, and the chain reaction immediately gets bigger and bigger and bigger. So if you completely neglect the delayed neutrons, and you still have a chain reaction, so you chain reaction based only on the immediately released neutrons, that's prompt. You're above the prompt critical mass, and you can have an explosive chain reaction. It just goes off to infinity in a fraction of a second. If you have a chain reaction that is self-sustaining and maybe even growing, but it requires the delayed neutrons to participate. You have to wait for the slow guys to come in to have enough neutrons produced in each generation to have a building reaction. The reaction builds very slowly, and so that's delayed critical. You're above critical mass, but you have to wait for the delayed neutrons to show up for the chain reaction to finally exceed break even and build up. And the result is the building up is very slow. It takes minutes, maybe more, to get stronger and stronger and stronger, because you need the slow guys to show up to keep on contributing. And nuclear reactors operate in that regime. They assemble a critical mass of material, but a delayed critical mass, not a prompt critical mass. The chain reaction requires the delayed guys to show up, and so it's much more controllable. It builds slowly, doesn't build in microseconds. It builds in seconds or minutes. And if it gets dangerously strong, they can clamp it down. They can shut it down, in principle at least. You okay with the idea of the delayed neutrons? It's the slow things showing up. I'm sort of, what is going on in the nuclear reactor as time goes on is complicated. It includes these delayed neutrons showing up. The delayed neutrons have the effect that they allow you to be above critical mass with this long-term process. They also, those other things sitting around inside the nuclear reactor also can absorb neutrons, and they become, therefore, reactor poisons. They're referred to as poisons because things that absorb neutrons tend to shut down the chain reaction. They gobble up the neutrons that were involved in continuing the reaction. So if you put a lot of those poisons in, you stop the reaction. And the reactions are controlled, actually, with poisons, but the poisons are normally held in what are called control rods, things that you can put in or take out so you don't permanently poison the reactor. And as long as they're in this controllable form, as rods you can put in and take out, the reactor runs normally. If they become dispersed in the reactor material, which happens when the reactor has been run for a long time and it's created its own poisons by accident, just the shattered nuclei that were produced by the reactor include reactor poisons that absorb neutrons. And reactors have been run for a long time and have accumulated a lot of neutron-absorbing bad guys in them, are hard to operate. And that has been a problem for some of the disasters, of the nuclear disasters too. So what else do I need to tell you about this? So the way that they operate a nuclear reactor is they assemble enough material that it would be certainly above delayed critical mass, so that it begins to develop a chain reaction that gets stronger and stronger, but takes a very long time scale for it to build. They control that reaction with control rods. So they normally have it, the control rods, when they're taken all the way out, that might be dangerous. That might allow you to go not only to delayed critical mass, but all the way to prompt critical mass, meaning that even with just neglecting the delayed neutrons, you have enough neutrons created with each generation to have a growing chain reaction. That's bad. You do not want prompt critical. That's for bombs. That's not for reactors. So they will bring in the control rods to the point where they will not, the growth rate of neutrons in the reactor is slow. If they take the control rods out too far, the growth rate of neutrons is too fast, too dangerous. So they're balancing the control rods to try to keep the growth rate of neutrons modest. What else? They run it. They let it run the chain reaction. If the chain reaction gets a little too strong, they put the control rods in further to suck up neutrons and slow down the reaction. If the reaction gets too weak, they pull the control rods out to get the reaction going more aggressively. And so it's always a balancing act. Control rods in, control rods out, trying to keep the reaction rate at a sort of steady pace. And while this is happening, heat is being released into the milieu of the reactor, typically water. And that heat is then taken out in the water, which entered at one temperature and has suddenly become 100 degrees C hotter, perhaps. It's taken out, it's used to generate electricity. That's a whole other story. Generating electricity with hot water is just, it's classic. People have done that, whether it's coal-fired, natural gas-fired. I mean, there are zillions of electric generating plants that use hot water, boiling water and steam to generate electricity. And the nuclear reactor just generates hot water and steam. All right? This is just my story about the delayed neutrons make the reaction controllable. All right, so, I won't ask that one either. I think just to finish the stories of these reactors. So these are all thermal fission reactors that I've described at this point. They use the moderator to slow down the neutrons. The uranium-238 therefore becomes kind of a bystander. The 235 gets used up. They gradually accumulate fission fragments, lots of fission fragments. They get depleted on uranium-235. Believe it or not, you actually can use a good fraction of it up. So the fuel rods develop they get sort of spoiled after a while. They don't have a lot of uranium-235 left in them, which is unfortunate because now the chain reaction is harder to keep going. And they start to accumulate things you don't want in them, like things that absorb neutrons. So they have to be reprocessed periodically. So, and part of this, telling you this, apart from just talking about physics, is that this is part of your world. You read about this stuff or could read about this stuff when there aren't other things to read about in the news. The reprocessing of nuclear fuel, the dealing with nuclear fuel both before and after its use, they're big problems or big issues for society. I won't say problems, but you can imagine that when you put in pristine fuel, it's mostly uranium in some form, maybe as an oxide. Uranium, the metal burns, so they put in uranium oxide, which doesn't burn. The oxygen just is irrelevant. But eventually, the uranium-235 in those rods has been used to some extent. They have things in them that you don't want, both radioactive fragments and fragments that absorb neutrons. So they have to reprocess them, get the crud out, clean up the uranium. It might not have enough uranium-235 left to work with, so you might have to discard it altogether. And what you do with this stuff, because it's pretty radioactive, is a big deal. And we're still struggling to figure out what to do with nuclear waste. The fact that it's still got radioactive stuff in it means that it's still generating heat. So fuel, even after it's no longer part of a chain reaction, it has lots of radioactive things in it, often with relatively short lifetimes. And as they decay, they release energy, and energy typically becomes thermal energy, and things get hot, so you have to keep them cool. That was a huge issue with the Fukuyama Daiichi disaster, which I'll get to shortly. What else? Okay. These are the thermal fission reactors. The other reactors that are around, the name seems to evolve because it's got sort of political ramifications. They were at one point called breeder reactors. Now I think they're called more fast fission reactors. It is possible to make a reactor that operates with fast neutrons. Using the slow neutrons allows you to operate with nearly natural uranium. And I should say, if you use deuterium as the moderator, you can actually operate with natural uranium because it's so efficient and it consumes so few neutrons, like none, that it's possible to make a reactor that uses ordinary uranium right out of the mine. If you use any other moderator, that moderator consumes enough neutrons that you can't quite run a chain reaction with natural uranium, so you have to use slightly enriched uranium. So most reactors use slightly enriched uranium, and they use water as the moderator. There are or have been carbon-moderated reactors around. They have to have a separate cooling system. The carbon obviously can't be used as a coolant because it's not a liquid, it doesn't flow. You can't get it out of there even though it gets hot. All right, so there is a big market for slightly enriched uranium in the world. And so there are facilities for slightly enriching uranium, surely in many places at this point. The other possible fuel for nuclear power is plutonium. It can be made in vast amounts, so it's potentially very inexpensive, but it's a proliferation hazard in that somebody who gets hold of 10 kilograms of plutonium can make a bomb. It's just the way, that's just the way it is. So, nonetheless, the world has some of these fast fission reactors, and what they are, they don't use moderators. They use highly enriched uranium to operate. So they go, well, we can't get the uranium-238 out to be invisible by slowing neutrons down. We'll run with normal fast-moving neutrons. The cost of which is that we have to have a lot of concentrated uranium-235 around. But the advantage is that the fast neutrons hitting uranium-238, which they do have in there to some extent, turns it into plutonium. So the reactor, in operating on uranium-235, produces plutonium, which can then be used as a fission fuel. So that was the idea of the breeder reactor, is that you can run this reactor and actually create more fuel than you started with, because you're transforming a useless material, uranium-238, into a useful material, plutonium-239. Apart from it being a proliferation hazard, because you don't really want to have a lot of plutonium around, or that's a big concern. The other part is you can't use water as a coolant because water is a moderator. It'll slow neutrons down and it'll mess up your reactor. So they use other coolants like liquid sodium, which can carry heat nicely, but doesn't stop the neutrons. All right, so you may over the years hear talk about fast fission reactors, breeder reactors. They're controversial, the whole idea, because the fuel that they are producing is plutonium. And if you can keep it under control, you can keep track of it all, fine. But if you lose some, it's dangerous. Okay? Any question about the reactors in general? I mean, I think I've said my piece about the reactors. Well, let me tell you about the famous disasters. Obviously, the spent fuels and all that stuff you want to be careful with. It's a radiation hazard. Plutonium is a proliferation hazard. All right, in general, the reactors, what makes them in general so controversial is you want them to be stable in concept so that almost nothing you do will cause the chain reaction to get out of control. You want the systems to be redundant to the point where one failure or even two failures won't cause a disaster. And it's tough. It's tough to anticipate all the ways things can go wrong. And you want the reactors easy to shut down quickly and as completely as possible, which is not completely, alas. You can't just like turn off all the nuclear activity in one of these reactors. You can turn off the chain reaction, but there's still a lot of radioactive stuff around. So, I'm there. So the famous disasters, just to walk through them a little bit. The first one was before even my time, way back in the dark ages. Wind scale. It's in Britain. They had a carbon-moderated thermal fission reactor. So that what I talked about, you had lots of semi-natural uranium sitting around, and they were slowing the neutrons down with carbon, and having a dandy old nuclear chain reaction that they had under control. Everything was good. The problem is the neutrons, whenever they hit one of the carbon nuclei to slow down, that affects the carbon nucleus, right? It's getting really smacked. And the result is that the carbon, which started out as graphite, like in your pencil lead, ordinary graphite, lots of this radioactive, radiation exposure had damaged the crystals. They are really messed up by having been, the nuclei had been knocked out of place and then resettled in some new location. And the material actually had a lot of extra energy in it, in the form of it being a disordered crystal. It wasn't crystal in the same way it was supposed to be. So it's got a lot of stored energy where things have been pulled out of place. And they knew that they had to to allow it to go back to its normal crystal structure periodically, a process known as annealing. And annealing is used in lots of situations where you want to bring something back to its simple situation. You heat it and try to let thermal energy allow everything to settle inside. They did that to the carbon, and it released its energy so aggressively that it overheated. So a little heat went in, and suddenly the carbon got really hot, caught fire. And so it caught fire, and so the carbon, which was not only carbon, but it had lots of radioactive crud in it, caught fire, and it spread radioactive stuff all over the countryside in Britain. So it's a little bit after World War II. Not good. All right, so that was one accident. Second accident, which I do remember, 3 Mile Island. The nuclear reactor, when it's operating, is producing a lot of thermal energy. And that thermal energy has to be carried off in water. And the water that actually is passing through the reactor tends to accumulate a lot of radioactive junk in it too. So they don't let that water actually leave the reactor vicinity. They instead put that water on one side of a metal surface and allow heat to flow from that very hot, somewhat radioactive water through the metal surface to ordinary water that's clean. And so there's a heat exchanger, in short. Heat is exchanged from water that actually serves as the coolant of the reactor to other water that's used to generate electricity. And that's typical of most reactors. They don't actually take the water from the reactor and send it out into the drinking fountains. They keep it in closed loops, and they move the heat from dirty water to clean water. All right? One of the pumps on the water that was involved in the power generation side, one of the pumps failed, and only what happened was the reactor was not able to get rid of its heat fast enough. They lost the sequence of events. There's also a valve failure with bad indicators, as I recall. So they lost the ability to get heat out of the reactor core fast enough. They turned off the reactor. The chain reaction was gone, but there's a lot of radioactive crud still remaining in there, decaying, producing those delayed neutrons, for example. It's still there, and it generates a lot of heat. And if you lose the ability to cool, first off, the water gets hotter and hotter. The water that's in there gets hotter and hotter and eventually becomes steam. The pressure builds and builds and builds, and eventually you can't contain it. So they lost cooling water, and they got parts of the reactor core essentially uncooled with no way of getting rid of heat, and it got hot enough to actually damage the solid material. So as far as I know, then the parts of the core of 3 Mile Island, that reactor melted in effect. And once that's happened, you sort of can't deal with it. It just sort of, to an extent, you have to wait out the radioactive stuff that's in there. They're almost untouchable. They're working on robots to try to go in and deal with these disasters and go and play with the junk. But even the robots get fried by the radiation. So it may be that you just have to leave them there for 100,000 years. And by that time, the radioactive decay will have reduced to the point where machines can deal with them. All right, Chernobyl. This one I certainly remember. This was, they did this, I wouldn't say deliberately, but this was a man-made disaster. The design of the reactor was bad to begin with. It used carbon as its moderator. So a lot of that era, Soviet Union thermal fission reactors were graphite moderated. But they also had water as a coolant. And the water was also acting as a moderator. So they were, in effect, over-moderated, meaning they had plenty of moderator to slow the neutrons down, and they had extra. So not only were they slowing the neutrons down, but they're actually absorbing more than they needed to, because water, after all, does absorb some neutrons. So they had an over-moderated reactor. It had run recently for a long time and was full of neutron-absorbing poisons. And so they were mucking around with the safety system. And they turned off the chain reaction, and they tried by putting the control rods in, and then they took the control rods out to try to get the reactor to start creating a chain reaction again, and they couldn't get the chain reaction going. Why? Because it was so filled with these neutron-absorbing poisons that the chain reaction was just having trouble getting started. The neutrons just kept getting gobbled up by the junk that had accumulated in the nuclear fuel. So they just kept pulling the control rods out, more and more and more. Nothing, and then something. And so they apparently, the chain reaction kicked into pretty high gear pretty quickly, and they realized they had the control rods too far out. And the control rods were motor driven and would take something like 20 seconds to get back into place, and they didn't have 20 seconds. And the chain reaction built so quickly that they went past delayed critical. They went into prompt critical. They were able. The chain reaction was first step before this. The water boiled. The chain reaction started to build up. The water boiled and left the reactor. And when that happened, the water, which had been absorbing neutrons, stopped absorbing neutrons. It was over-moderated. The water was actually causing trouble, was squelching the chain reaction. When it left, the chain reaction went, wow, this is great. And it built so quickly that it actually went prompt critical, which is like a bomb. Each generation was one generation was begetting the next generation in fractions of a second instead of in minutes. And so it was building on the second by second rate. Consequently, it overheated, went white hot, melted, burned, total disaster. The world is still dealing with it. I mean, there's a substantial region of the Ukraine that's uninhabitable because of that disaster. And then very recently, they re-entombed the reactor itself to keep all the radioactive crud in it for the next 100 years or maybe 1,000 years. But it's going to be an ongoing process to deal with for generations. John? Can you get rid of radioactive stuff by bombing it? Now the problem, it's very hard to get rid of because you basically, it's sitting there waiting to pop, and the only way to pop it is to hit it with something that can actually, that can force the breakage. And you can do that with accelerators. It is possible to sort of burn up radioactive stuff in accelerators. And there are proposals to make reactors that are accelerator based so that they can burn their own trash. But it's very hard to get rid of. Chemical effects have chemistry has no effect on the nucleus. You can't get its attention with chemistry. You have to go actually into the nucleus with wrenches and hammers, and that's hard. So you mostly just have to wait. You have to wait out the radioactive stuff, or people propose like launching it into the sun. But you know, what if the rocket crashes? I mean, it's just terrible trouble. Tokamura was another human-made disaster. People were processing uranium, a uranium solution, and uranium and water, always a dangerous thing because water is a moderator, right? It will slow neutrons down. So whatever you're doing, having uranium and water runs the risk of getting a chain reaction going. And some bright person decided that instead of making one batch at a time, they would make 6. I think it was 6. They just scaled up man, I can go home early, wow. And so they mixed up too big a batch, and they went above the critical mass. And they had a big basin they had a nuclear reaction in a basin, and it would undergo the chain reaction. The chain reaction would build and build and build, and it would get hotter and hotter, and as it did, the liquid expanded, and it went below critical mass, and then it would cool down. And then it would get denser and denser, and the chain reaction would start again, and so it was pulsing on and off. I forget whether this was like every few minutes. There would be a burst of radiation every few minutes, and eventually they figured out how to shut this thing down. I forget what they did it, but it was like, yeah, it was another really bad disaster. You know, I don't think anybody was killed in it, but it was just, oh my God, what did you do? And then the famous one recently that surely you do remember, where an earthquake triggered a tsunami that inundated the Fukushima Daiichi nuclear plant with 4 reactors and a bunch of storage ponds where they had old fuel, all kinds of stuff that needed constant tending. They shut off all the reactors, so the chain reactions were all gone, but there was so much radioactive stuff still present in the reactors, in the cooling ponds. They lost the ability to cool all that stuff. And just because there's no chain reaction doesn't mean it's not making a lot of heat. And so these things all overheated. Some of them melted. They're now fiercely radioactive venues that recently they've been trying to go in and just survey with robots. And the robots get fried. They put in radiation-hardened robots that should be able to survive the intense radiation. This is stuff that would kill a person in seconds. But the robots manage to make it for minutes or maybe more, but not much more. They just can't tolerate all the neutrons and other shrapnel that's coming out. It just cooks them. So this was unanticipated, the idea of losing all their electricity and therefore all their ability to cool even just spent fuel sitting in a pond. Evidently people had not anticipated that possibility. And it's now another wasteland in northeast of Tokyo. All right, I think that's good enough for nuclear reactors. And on Wednesday I will talk about radiation and imaging, medical stuff.